Hey, what's up YouTube? Seth Lake here with a new series of videos we're doing on the engine and really the power plant system of a piston aircraft. So as an examiner, one of the things that I ask about is engine systems. So I think the best way to learn this is to break it down piece by piece. Because conceptually, I find a lot of pilots know how the engine works on a piece of paper. They've seen maybe a crankshaft and an engine, and they know the suck, squeeze, bang, blow mantra of how a piston engine works. But when I start asking about failure modes and like how big these things are, the fundamental knowledge isn't there because it's really hard to learn an engine in a two-dimensional space. So we're going to do these series of videos, and we're actually going to break down an actual piston engine that's really common in the general aviation fleet, piece by piece, and talk about the individual aspects of it, and more importantly, the failure modes that you can encounter with these engines. So stay tuned. All right, so we're going to start by talking about the crank and the cam. Like I said, the first thing we're going to do is the crank. So that's what I'm holding right here. This thing is pretty heavy. I've got a scale right here. We're actually going to weigh this and see how much it actually weighs. So this is weighing in at 33 pounds. So this crank right here, 33 pounds of just solid steel. So they start with a solid block of steel and they machine this down to see what it is right here. Now you can see that it's not just a straight shaft. These things that stick off to the side here are where the piston rod's attached to. We'll actually talk about the piston rods in a later episode, but these are where your pistons attach. The main parts of your crank that make contact with the case are here aligned with the center of the shaft. So you can see we've got a large place where a bearing goes here, here, and here. So you can see how it interfaces with the case. I've got a case right here. I'll tilt up so you can see. But these locations rest in these three locations here on the case. So that's actually what's making contact, kind of the main part of your crank. Those other places being where the piston rod's attached to. So the force of the pistons going up and down is translated into a circular motion. So that's why they're set up in kind of an eccentric way. So an up and down motion can cause a circular rotation of the crank, which is what we want, because here at the end of the crank, you can see this bolt pattern right here is where our propeller connects to. So I've got a propeller sitting right here. You can see that the 6 bolts that were right here interface exactly with where this propeller goes. The interesting thing about this crankshaft, or another interesting thing about the crankshaft, is that it has these small holes. You've probably seen in the video. These small holes are drilled into the crank and actually allow oil to pass through the crank's body into other parts of the crank. So we'll talk about it when we talk about our case, but we actually have pressurized oil that's going through this entire crank. So this isn't a solid object actually. There's actually a few holes in those. And the holes, the way they're designed, they actually add structural integrity to this crank, making it stronger. The other thing that you'll notice is if you look down the center there, on that close-in shot, you can see that the end of this crank is hollow. So we only see these types of hollow cranks on constant speed propellers. If this crank was going on a fixed pitch propeller, there would be either a solid crank here or an actual plug that would go in and block this hole here. In fact, that's a common problem with 0360 or cranks that are hollow in nature that have a plug in. If that plug's not properly installed and sealed, you could actually have moisture build up here and cause corrosion inside that hollow portion of the crank. So that's a concern for aircraft owners if you have that type of crank. This type of crank, of course, is coming off of a travel air, which is a constant speed propeller. So the way we deliver oil to our propeller is actually through this crank, which I think is pretty amazing because we have a crank here that's spinning around at about 2,700 RPMs. And while it's spinning at 2,700 RPMs, we were able to engineer a way to feed oil through something spinning around at 2,700 RPMs up to another thing that's spinning at 2,700 RPMs and move a piston back and forth. Just the amount of engineering there is pretty incredible. And also, this technology was developed in the 1920s. So it's not like super advanced technology. It's just what we were able to do in the 20s with slide rules and paper calculations. I think it's pretty incredible. So that's our crank. Now, also in our engine is a camshaft. The camshaft is a lot smaller. We'll go ahead and weigh this one as well, just to see. The camshaft is 2.5 pounds. The camshaft obviously is a lot smaller than our crankshaft, and it serves a lot different purpose than the crankshaft does. Remember, the crankshaft has to be really strong because it's what's transferring all the energy that our pistons are building, transferring that power to the propeller. So the camshaft actually sits at the top of the engine, and its purpose is to time the opening and closing of the valves so the engine runs properly. Now, the way this works is the camshaft sits at the top of the engine. And I say the top because as we're looking at this, the engine case itself here would be sitting in the engine like this. So the cam would be at the very top of the whole thing, up at the top of the case. The crank sits right below . So here's how our crankshaft and our camshaft sit on the airplane. I've got it slightly tilted here, but you can see the crank spins around in the engine case here. And here at the back there'll be two gears if this engine were put together. Something that looks like this, and that would fit just like that on the back of the case, which is surprising. That's not a very big gear, but don't worry, that gear isn't the thing that's turning the propeller or the engine around, but that gear is critical for the engine to operate properly. The gear that would be connected to the crank would be another one. I don't have the appropriate gear on me right now, but it would be something like this, and it would sit here, and that would actually be big enough to interface with another gear. So as the crank spins, it would cause the cam to spin as well. So let's talk about the cam's job, because it's actually a little more complicated than what the crank does. The crank is pretty simple, right? It's just a strong piece of metal that transfers that horizontal motion into a circular motion, delivering power to our propeller. The camshaft, that has these eccentric little lobes, so those are called cam lobes. Now each of these are kind of egg-shaped. And the reason they're egg-shaped is that they make contact with this little guy. So this little guy is a lifter body. Now this lifter body sits inside of our engine case. You see right here. So this is the little lifter body. And what this lifter body does, it has this little spring thing inside of it, and all lifter bodies are a little different. So this is a Lycoming 0360. Continental are going to have different types of lifter bodies than Lycoming and different engine models, but they all serve the same purpose. What they do is they ride along those eccentric lobes of the cam. Inside the lifter body, we have this little doodad, and it's actually has a lot of spring force there. And you can see there's tiny little holes in this whole contraption here. We've got little holes everywhere. And the reason is there's actually pressurized oil that's being sent through this lifter to make sure everything's lubricated. Because this lifter, if let's say your crank is spinning at 2,000 RPMs, then your camshaft is going to be spinning at 4,000 RPMs, and that up and down force is going to be hitting this lifter body. So you can kind of see right here, how this works is you can see the lifter body sits down in the case, and I'm going to push this lifter body out that's right there. And you can see as this crank spins, it's going to hit that lifter and move it. So you saw how the lifter kind of interfaces with these cam lobes. Well, each time this lifter opens, it actually goes through, it begins our valve train and opens a valve on the cylinder. Now, to learn what that is, you'll have to stay tuned to the channel because our cylinder episode will explain in detail what these lifters are actually doing. So stay tuned for that. For now, let's just talk about this cam. So we know that this cam's job is ultimately to open up the valves of our engine. Now again, we're going to talk more about valves on our cylinder episode, but each cylinder has 2 valves, and this engine has 4 cylinders. So 4 times 2 is 8, so we have 8 valves on our engine. Well, if you count up these lobes, we only have 6 lobes. So it doesn't quite make sense because we have 6 lobes, but we have 8 valves. So what must be happening is that 2 of these lobes are actually doing double duty. They're opening both an intake and exhaust valve each. You can sort of see how this works here, because in our case here, so this would be the left-hand side of the case that we're seeing, and we only see lifter bodies for 4 valves, the 2 cylinders that go on this side. And you can see that these lobes interface with those 4 valves, or lifter bodies. You can also see in this case how these 2 lobes don't make contact with anything on the left-hand side of the case. So these 2 lobes don't make contact with anything. If we look at our other case here, you can see that there's no lifter bodies here, lifter body here, and a lifter body at the very front of the case. See, this is the front of the case here. You can tell from this is where the propeller would go. So these 2 lifter bodies on this side case, there's no lifter bodies there. So if the cam's over here, now we can see that the 2 that didn't have any contact on the left-hand case have contact on the right case. So based on that, we know that these 2 lobes right here are actually doing double duty. So they're, instead of just hitting 1 lifter body per rotation, they're hitting 2 lifter bodies per rotation. So that's a little bit of an engineering problem, right? Because if you think about over the 2,000 hours of the engine, on average operating, oh man, I'm fixing to do some math that I'm not prepared to do, but we think of the engine operating for 2,000 hours on an average of 2,300 RPMs. That's a lot of rotations. And instead of making contact with 1 metal surface, these are making contact with 2 per rotation. So what can happen in these Lycoming engines, and really any piston engine, is you can have uneven wear, where the double duty lobes start to get worn down faster than the single duty lobes. If we were able to measure this really precisely, I'm betting we would probably see uneven wear, where this lobe is slightly shorter than this lobe. The reason that matters is if this lobe can't move the lifter as much as the other lifters, then that means either our intake or exhaust valves aren't opening the same amount, which means our engine is not making the horsepower that it needs to make. So on an old engine, when they say an old engine doesn't make the same horsepower it did coming out of the factory, the reason that is because of these cam lobes, or one of the reasons. Because these cam lobes wear down over time. We've got metal on metal fatigue happening, and especially you can actually see on this lifter body, this one's in pretty bad shape. This is from a much older engine. You can see how that looks kind of like the surface of the moon there, and you can imagine that the impact force hitting this is almost like sandpaper. So each rotation starts to wear down those cam lobes and make them smaller and smaller and smaller. So if you're flying an old engine and it feels a little sluggish, this could be one of the reasons, is your intake valves might not be opening enough. The best way to explain that is it's like if you're out there doing sprints on the basketball court and you have a piece of tape over your mouth, or you've got one nostril blocked. You're trying to sprint, but you can't get the breath that you need in your lungs because it's partially blocked. That's essentially what's happening, is our engine intakes start to become blocked, and our engine can't get the air that it needs to make the combustion that it should, so it's not making the horsepower that it's rated to make. All right, the other major issue with all of these components is they're spinning at a high rate of speed, and you should be thinking, wow, this is metal on metal contact. How in the world does it not just grind itself down to nothing in a relatively short time? And the reason is this. Now this is a bearing. I think most people think of bearings as like a bearing you'd see in a roller skate, like a set of roller bearings that move around, and anyway, that's not what an engine bearing is. It's a piece of metal, and we precisely machine this piece of metal to precisely fit in the case of the engine, and also fit along and interface exactly with our crankshaft. And you'll notice that this bearing has some holes in it, and these holes line up with the holes in our case, and they allow pressurized oil to enter into this bearing. And what happens ultimately is, as we're flying, this crank isn't making contact with metal. It's actually riding on a cushion of oil, a very thin cushion of oil. So ideally, a properly running engine with proper oil pressure has enough oil pressure where it actually is a liquid bearing almost. So this liquid bearing prevents metal on metal contact. And that liquid bearing is only made possible by oil pressure. So when you're checking oil pressure in your engine, what you're actually checking is the pressurization of these three locations in your engine case. If these three locations lose oil pressure at any time, that liquid barrier disappears and you start to have metal on metal contact. The temperature of the engine will increase rapidly. You may not see that. We don't have an engine temperature gauge. We have an oil temperature gauge. We have an oil pressure gauge. Most planes have a cylinder head temperature gauge and an exhaust gas temperature gauge. Those are the only four temperatures that we typically have. The temperatures are going to increase in the case itself. Now that might translate into high oil temperatures, but it might not. There's been several cases of these bearings failing and no subsequent oil temperature increases have been seen, or cylinder head temperatures. Because remember, our cylinders sit 90 degrees offset of our crank. So our cylinder head temperatures don't tell us anything about the temperature of this bearing right here. The only gauge that we have that's telling us about this bearing indirectly is our oil pressure. So if you ever lose oil pressure, you're looking at an impending failure pretty quickly, because what's going to happen is, as this crank spins, you can actually hear it sort of grinding on that bearing. And you imagine this is just half the bearing. There would be two around here. This bearing is going to heat up. It's going to reach its melting point before this crank does. So this bearing is going to fail, and it'll start to slip, and then it'll reach a temperature, and the crank will as well, where the crank actually starts to fuse itself to this bearing, and the engine is just basically eating itself. Eventually you're going to have a catastrophic failure where the engine will seize up completely. So catastrophic failure is obviously the worst case scenario, but it's not all that could happen, right? We could also have, let's just say you did an oil change, you didn't do a proper leak check, maybe didn't get the filter on properly, and you're leaking out a little bit of oil as you taxi out. This oil leak gets a little bit worse, and before you know it, by the time you're doing your run-up, most of your oil is gone, and you're down below your minimum oil pickup, and you start to lose oil pressure. So about the time you take off, you start to notice, hey, maybe my engine's running a little bit differently, or I finally noticed that the oil pressure has indeed dropped to zero. Already, even at 1,000 RPMs, which is your normal idle speed, this bearing has been sitting unprotected, getting ground down by this crank. It's going to cause a lot of heat buildup that could actually deform this bearing here. Now it could deform the bearing, it could damage it could damage your crank, but you think, hey, I caught it before it went to 0 or completely 0, so I'm probably good to go. The insidious thing about this is even though your engine appears to be operating normally, after you put oil back into it, tighten down the oil filter properly, and you go back to running your engine normally, what happened though is that you've caused fatigue in this bearing. You caused damage in your crank, and it could have a premature failure later on in its life. It could be 5 hours from then, it could be 500 hours from then. You don't really know, and that's kind of the problem with cranks and bearings and this internal, this lower end of your engine, is there's no way to really check it, right? When I pre-flight my airplane, I can walk out to it and I can move the flight controls around and I can check all the surfaces. My engine, on the other hand, I can't really pre-flight it other than operating it. And if I don't know how it's been operated, if I don't know that it's actually experienced a loss of oil pressure, I may not know the internal conditions of these critical components until they actually fail. And when they fail, it's typically going to be in flight, and it's not going to be a very good day for you. So you really want to make sure you're watching that oil pressure at all times. So bring that oil pressure into your scan. If you ever let it drop to 0, you might do irreparable damage to your engine, and unfortunately the only way to fix this is to take the engine completely apart, check everything, and put it back together. That's a pretty costly endeavor, so we want to avoid that. All right, so we've talked about the crank in detail and the camshaft in detail. On the next episode, we're going to talk more about the case because it's really important, an important component of the engine, so you need to stay tuned for that. Subscribe and like the channel if you haven't already, and stay tuned for the next episode. See ya.